Hi there, my name is Christopher Hojny and I'm an assistant professor at Eindhoven University of Technology. In this short video, I want to present my research interests, but before going into the details, I want to briefly discuss three optimization problems that I'm working on, at least implicitly. And the first problem on the left-hand side is the make-span minimization problem, in which we are facing the task to assign jobs to identical machines while minimizing the processing time of the longest running machine. The second problem in the center is the bin packing problem, which requires us to pack objects into rectangular bins while minimizing the number of necessary bins. And the last problem, the stable set problem, asks us to find the maximum number of pairwise non-adjacent nodes in a graph. Although all of these problems look rather differently, they actually have a common ground. Namely, they can be modeled using the framework of mixed integer programming. And next to this common ground, they have a second commonality, namely, all of these problems contain symmetries, which means we can take one of the solutions that we have derived so far and we can create another solution that essentially looks the same but is slightly different. So for instance, in the scheduling problem, we reassign the jobs from one machine to another machine. In the bin packing problem, we can reflect the assignments inside a box and we can also exchange identical items. And in the stable set problem, we can apply graph automorphisms to derive alternative solutions. And in my research, I'm working on algorithms and techniques that allow us to make use of such symmetries when solving mixed integer programs. To be able to understand why the handling of such symmetries is actually important, let us briefly recall how we actually solve mixed integer programs, and I want to illustrate this using the stable set problem, in which, in a nutshell, we essentially start with an empty graph, and then we select one of the nodes of our graph and decide whether it is contained in the stable set or not. And this creates two subproblems that I've denoted here in this tree. And then we iterate this approach, for instance, by picking the problem on the right-hand side, selecting another node, and deciding whether it is contained in the stable set, yes or no. If we do this, we can, in the end, find an optimal solution of the stable set problem. But as you might can imagine, we can possibly create a lot of subproblems until we have actually found an optimal solution. And if we have a closer look into this branch and bound tree that we've created here, then the two problems on the left-hand side are essentially the same. We can transform one of these subproblems into the other just by applying a rotation of 90 degrees, which also means that all the solutions that we find in one subproblem have a symmetric counterpart in the other subproblem. And we can accelerate branch and bound by removing one of these subproblems from our list of open subproblems. And the aim of symmetry handling is to exploit this in a more general context such that we can avoid making symmetric decisions when solving a mixed integer program. And in my research, to make it pictorially speaking, I am looking for algorithms that prevent that we can find these symmetric solutions. That is, I'm looking for ways to accelerate branch and bound solvers. To make this a little bit more concrete, I'm working in my research on symmetry detection and handling algorithms. I'm focusing on permutation symmetries, which corresponds, for instance, to exchanging identical items that we assign to bins, or geometric symmetries like reflection symmetries that also materialize in the bin packing problem. And once we've detected these symmetries, I'm also looking for algorithms that either exploit the symmetry group structure of the concrete group that we are given in our mixed integer programming instance, or if we do not have any structural insights, I'm also looking for algorithmic techniques that allow us to exploit arbitrary symmetry information. As you can imagine, such algorithms are only beneficial if you can also test them in practice. And for this reason, I implement most of my techniques also in the open source solver Skip, which means that whenever you solve a mixed integer program using Skip, it automatically will apply my detection and symmetry handling algorithms to accelerate the branch and bound procedure. Next to symmetry handling, I'm also interested in quantitative properties of mixed integer programs, which means I investigate how many inequalities do I need to represent a specific set as the feasible region of an integer program, or how large do the coefficients need to grow in such a formulation. And next to these theoretic investigations, I'm also interested in deriving specialized mixed integer programming techniques that allow us to solve more concrete problems faster. And I hope that this short video gave you a good impression of the topics that I'm working on. And if you want to know more about me and my research, please feel free to reach out to me or to check out my website.